Bismillahirrahmanirrahim. Assalamualaikum and hi everyone. So today our group will present our test 2 for the instrumentation subject. So the topic of our presentation is temperature measurement system using LM35 sensor with signal conditioning. So first of all, uh, the understanding of the LM35 sensor output. The LM35 is a precision temperature sensor that converts temperature directly into an analog voltage signal with a sensitivity of 10 MV per Celsius. For the example, 30 Celsius will get 0.3 volt, 50 Celsius will get 0.5 volt, 100 Celsius will get 1 volt. The output is highly linear, which making it easy to interpret. However, the voltage range is very small, which reaching only about 1 volt at 100 Celsius, which presents challenges when interfacing with microcontroller like Arduino that expect a 0 until 5 volt input range. There are four key problems with raw LM35 output. The first one is signal noise issue. Output signal from LM35 is easily affected by electrical noise and interference from the environment. Second, limited ADC utilization. Arduino ADC utilization operates over 0 until 5 volt range, but the LM35 only outputs up to 1 volt at 100 Celsius. Third, only 20% ADC range used. Because LM35 output is limited to 1 volt, so only 20% of the Arduino ADC range is utilized. The last, reduced resolution and accuracy. The low ADC utilization results in fewer usable digital steps, which leading to lower measurement resolution and reduced accuracy. So the third slide tell about why signal conditioning is needed. First of all, enhance signal quality to improve measurement accuracy and reliability of temperature readings from the LM35 sensor. Second, it can maximize Arduino ADC range utilization. LM35 only use 20% of the 0 until 5 range without conditioning, which reducing resolution. Last but not least, it can reduce electrical noise for stable, consistent readings by filtering high frequency interference from the sensor output.
So for the next one is I will continue for the signal conditioning method. So we use two features yet. That is low pass filter and non-inverting amplifier, which is the gain is 5. So for the low pass filter, we remove the high frequency electrical noise from the LM35 analog output. Since the temperature changes slowly, only low frequency signal need to pass, and the noise is filtered out for a cleaner, so more stable reading we get. So for the non-inverting amplifier, amplifies the filter LM35 signal by a factor of 5 using the LM358 op amp. Expand the output voltage range from negative 0 to 1 volt up to 0 to 5 volt. So maximizing Arduino ADC utilization and improving the measurement accuracy. So for the next slide is low pass filter explain. So a low pass filter is used to remove high frequency noise from the LM35 sensor output. Since the temperature changes slowly, the actual signal contains only few frequencies. The LPF allow the low frequency signal to pass through while blocking high frequency electrical noises and interference. This result is a cleaner, more stable voltage signal before it reaches the amplifier stages. So the next one is non-inverting amplifier. So amplifier the filtered LM35 signal using the LM358 op amp with a gain of 5 boost the small sensor voltage, by example 0.5 voltage at 50 degrees Celsius to a stronger output 2.5 volt, making the signal more robust and reliable for processing. So we expand the effective output voltage range of LM35 to better utilize the full 0 to 5 volt ADC range of the Arduino, significantly improving measurement resolution and overall system accuracy.
Okay, now for the signal conditioning circuit flow. This is the slide shows about the complete signal conditioning circuit used in our temperature monitoring system. First, the LM35 sensor detect the temperature and produce an analog output of 10 mV per degree Celsius. Next, the signal pass through a low pass filter, which remove high frequency noise and provide a cleaner signal. The filtered signal is then amplified using LM358 non-inverting amplifier with a gain of 5, which increase the voltage from 1 volt to 5 volt. This amplified the signal. This amplified signal is then sent to the Arduino Uno, where the analog to digital converter process the signal. Finally, the Arduino calculates the temperature and displays the reading on the LCD. This signal conditioning circuit ensures the temperature measurement is stable, accurate, and also suitable for the Arduino processing. This is the Tinkercad implement of the circuit, and then the amplification example. For input signal at 50 degrees Celsius, the LM35 senses output of 5 volt, which only 10% of the Arduino 5 volt ADC range, resulting in low resolution and also a poor measurement accuracy. And then after amplification, the non-inverting amplifier boosts the signal to 2.5 volt, which is 5 times more gain increasing than the previous one, utilizing 50% of the ADC range for significantly improved accuracy.
Yeah, the next part is the result and conclusion. Yeah, after applying a gain of 5, the output voltage expands to match the Arduino ADC range. The result are the 35 degrees Celsius will become 1.25 volts, and the 50 degrees Celsius will become 2.5 volts. For 75 degrees Celsius will become 3.75 volts, and 100 degrees Celsius will become 5 volts. This allows the Arduino to fully utilize its 0 to 5 volts ADC range, improving measurement resolution and accuracy. In addition, the low-pass filter reduces noise and produces more stable temperature reading. Then, benefit of signal conditioning. Full ADC range utilization signal conditioning amplifier LM35 output up to 1 volt by a factor of 5. Uh, this maximizes resolution and measurement accuracy, turning a 30% ADC utilization into 100%, significantly improving the precision of temperature reading. Overall, the signal conditioning circuit successfully improved the quality of the LM35 output by increasing signal amplitude and reducing interference. In conclusion, the project demonstrates how signal conditioning enhances the performance of a temperature measurement system using the LM35 sensor and Arduino Uno. Okay, that's all from us. Thank you.